I echo Benjamin's thanks for you guys for attending the workshops and the conference, the symposium. I think it's going to be fantastic tomorrow. It is an extreme pleasure to introduce somebody who really doesn't need an introduction, but I will do it anyway. Somebody who is somebody I looked up for when I was trying to find my way through research. Approached him about certain ideas that I had, and convinced him to join me on a research project that hopefully we will be announcing more about in the near future. Robert Aish is a visiting professor of design computation at the Bartlett School of Architecture, University College London. Over the last 4 decades, Robert has played a pivotal role in the development of new computational technologies in architecture. As Director of Software Development at Autodesk, he led the recent development of the DesignScript language, a special end-user programming language for architectural computation. At Bentley Systems before that, he led the development of GenerativeComponents, which was used in the design of the Velodrome at the 2012 Olympics. He is co-founder of the SmartGeometry group, and through his teaching and publications, he has helped to create a vital bridge between architectural research, education, and practice. Robert studied industrial design at the Royal College of Art and has a Ph.D. in human-computer interaction from the University of Essex, and he's currently my partner in crime on a Leverhulme Trust grant that we are working on. Please help me welcome Robert.
Okay, well, thank you very much for such a warm welcome. Okay, do I press the screen? Yeah. No, we've got to change. Okay.
Sorry.
Oh, okay. So I had to change trains at Cardiff Queen Street to get a train to Cardiff Bay, and I was had 10 minutes. I was out with the laptop, beavering away on the presentation. Okay, so okay, I can see it here. Right, really good. Okay, so this is slightly different to what sort of normal presentation that I I give, but I'm not going to go for the sort of historical review of parametric design, although I am going to just chuck in a few slides. You may know that I sort of started working in shipbuilding, parametric shipbuilding in the late 90s, the Gdansk shipyard in Poland. This is Gdansk. After that, I designed the camera tools in MicroStation. And in fact, one of the projects is the Millennium Stadium in Cardiff. And my colleague at the time, Jay Parrish, was designing the stadium. And he said, I got this wonderful aerial photograph of the site, and I've got my model. Can you match the two? So we actually wrote a special photo match software where you locate points in the image and points in the model, and you press the button and out comes the solution. So that's my sort of connection to Cardiff. I then worked at YRM on things like the Waterloo Arch for Grimshaw's. It was essentially conceived as a parametric building, a variational building, but of course at that time it couldn't be built that way. So we did a sort of retrospective of it. You could pick up parts of it and move it around and everything updated. Then this is a KPF high-rise, which we did the first unfolding of to look at the planarity. The red polygons are the ones which aren't quite planar. So we were sort of rationalizing doubly curved high-rises. It's a pity that Mike Weinstock isn't here, because that's the first canopy designed with generative components at the Architectural Association, early 2000s, I should think. Marina Bay Bridge in Singapore, most probably you've walked across there, Nicholas. Also designed with generative components, and of course the Velodrome at the 2012 Olympics, designed with generative components. So that's a sort of very brief kind of like some of the things I've done and some of the projects that these tools have been used on. And I wasn't involved in the design of many of these things. I just wrote the software, and it was the software that was used in ways that I didn't sort of anticipate that by people who were completely independent, which is important, that other people can use your software. But I want to more reflect now on what's happened with computing in architecture. Is that readable? I hope so. Okay, so we've got these two dimensions, the sort of computational, the integrative, and I'm sort of calibrating the space with three Foster buildings, the City Hall, which I would characterize as being post-rationalized. It's a sort of egg shape. It was conceived as a sort of eggy kind of building, and then sliced up and unwrapped to make it constructible with planar quads. So that's a kind of example of a post-rationalized piece of architecture. Then there's the pre-rationalized. This is the Sage Center in Gateshead, where it was decided before the design work started that they would use toroidal geometry. And that, of course, meant that there was a lot of repetition in the design and actually made that design feasible. So that's a doubly curved surface. It's a pre-rationalized one. And then an example of what I would call embedded rationality, which is the British Museum roof, essentially by Chris Williams. And that's a sort of progression, I think. Essentially a sort of computational rationality strategies to harness physics. Actually, the computation dimension is not a time dimension at all, because the British Museum came first. But I'm organizing it. I'm organizing this quadrant in terms of computational dimension, and then we can sort of also argue that the British Museum is this intersection of things that happened in the sort of pre-computation era. If we go back to Fry Otto, grid shells, and back to Gaudi, maybe even to the Pantheon. And it's interesting to compare the Pantheon, which is sort of a monocoque construction, with a sort of skeletal construction of St. Paul's. But essentially you see a form-finding a kind of direction there from physical simulation to computational simulation. And then if we extend into the sort of negative quadrant, the disintegrative design, we have things like Eisenman's deconstructed, it's the Cincinnati School of Architecture. I think we had an Acadia there a few years ago, and things like Zaha's cantilever, and Metaballs, the BMW Pavilion by Bernard Franklin. And this is sort of like going off into a sort of sensorial computation where we're developing strategies that sort of apparently circumvent physics. So we've got this kind of distinction, and in fact, even into sort of fictional architecture where it's physics free. We don't have to build it. And of course, all these things influence. So if I've seen it in the video game or I've seen it in the cartoon, well, why can't I build a real building? So there's this sort of interchange between what is physically achievable and what is fantasy, because fantasy influences what you want to physically achieve, sort of feeding it back in. So we have this architecture as a sort of systems integration, with emergent sort of cultural implications. And you could argue that if you look at a Fry Otto building or even a Gaudi building or the British Museum, somehow it's communicating a sort of public understanding of science. Oh yeah, we've got this this catenary arch. Oh, I understand that if I have something in complete tension, I roll it over, I'll get something in compression. There's some understanding there, versus architecture which is purely sort of a cultural statement. Look what we can do. Essentially, something which attempts to circumvent physics. So it's really quite interesting, these kind of distinctions. So I want to look at the sort of Metaball example in a little bit more detail and sort of think about architecture at the interface between science and art. So we're going to have our sort of, I hope you can read that, sort of boundary, science space and art space. And I think if you go on the Bernard Franklin website, I'm sort of telling the story that is on their website that they started off with this idea of water droplets, sort of the physics of surface tension, but also the kind of cultural extrapolation of that. The water was something, pure and symbolic and clean energy, and it had sort of lots of sort of cultural implications. Okay, and then we sort of take that idea back into the science domain, and we create a computer simulation using sort of metaballs and Maya, and then that even that image, even though it's a sort of technologically created image, the image starts to have a sort of cultural life of its own, really. And then when we've got that, we take it back on the other side, and we have to actually engineer it and digitally fabricate it. But the fabrication and the engineering is something which is completely divorced from the physics, which was the inspiration for the design. And we end up with a building which I think, for me, is sort of really an allegory of science. And then we construct a narrative which brings all these ideas together in a very convincing, or the intention is to be very convincing. But actually, we've just crossed the sort of arts and science sort of divide 5 times in this story. There's I think there's some sort of irony here that the water droplet is essentially something which is incredibly transient. It only happens for a sort of a fraction of a second. But the building that we're trying to create is very permanent. And there's a sort of, I don't know, contradiction, a bit of a contradiction there. And so one could argue that the architectural idea of the water droplets is trying to sort of break out from its sort of physical constraints. We're using ideas that aren't naturally realizable as a building. And if we look at the definition of the word allegory, it's really a sort of a way of illustrating complex ideas in a way which is comprehensible to a lay sort of viewer or audience. So we have this idea of architecture existing as a sort of allegory of science, when the actual scientific principles used in its sort of in defining the configuration is completely different to the ones which are post-rationalized and actually are made in actually realizing the building. And then, architecture exists as an allegory of science. I think also this idea between power and enlightenment. And I was at the Fabricate conference where this building was discussed, and it's essentially it was described as an environmentally friendly petrol station or gas station, and it's sort of it's got sort of solar panels on the roof, and but I think that however enlightened the architectural intentions may be, it doesn't actually change the fundamentals. This is a gas station, and languages. We might have this architectural language, or we might even have the sort of the natural language of environmentally friendly. But language changes in the way it's by the way it is used. And essentially, this is if we do this, we're just devaluing the language. And then it exists between concept and realization. This is the City of Dreams Hotel by Zaha Hadid's office. And what struck me here is I met the people from Front, who are the fabrication facade designers, and I'm just like amazed by the asymmetry between the thoughtfulness that went into the realization and really the superficiality of the concept. Like, take this block and punch some holes through it. I just don't understand that somehow. And then maybe a bit contentious between faith and reason. This idea. This is the European Central Bank in Frankfurt by Co-op Himmelbrau and Bulling & Grohmann engineers. I actually talked to the engineers about this, and this idea that architecture doesn't have to be completely rational, but we're going to add in rational elements to it. It's just, so I looked at this building and I thought there's something really strange about it, because effectively it's two completely different design methods and philosophy combined in one building. This is from the Kopp Himmelbrau website, where they describe how they took this block and they kind of sliced it, like a lump of cheese with a wire, and then they took one side of it, turned it upside down, and positioned it on the other side. I mean, it's completely willful, cultural statement. Look what we can do. And then Bunning and Groen used sort of optimization and machine learning to produce this interesting vertical truss that holds the two sides together. And the analogy that I talked to the engineers about was really looking at the ship, which is HMS Warrior. You can go and see it in Portsmouth, which is this hybrid ship which combines two completely different kinds of technology and two completely different design methods. It's a wooden ship. I think when the naval officers wanted to have a fully mechanized ship, they went to the kind of senior admirals and they said, well, you can have it provided the ship also has sails and could, if all your new technology fails, then at least we can get the thing home. And if you think about it, it's about 1859. Sailing ships are coming to their peak, and here's this new technology, which is represented by here, and of course that took off, and steamships became the dominant form of transport. But if we think about it in terms of that same graph applied to architecture, essentially this building is at that intersection point between willful manual crafted design and computational design. And where are we going to? If we use the example of the ship, and extrapolate, where are we going to get to? So this idea that architecture is not completely irrational, but somehow if part of the building is rational, we can claim that there's rationality in the building, and then we can claim that even the rational bits have a subjective quality about it. It's though we want to have our cake and eat it. We want it to be more than rational, but also rational. So looking at this is the final one, which is in one of the articles I wrote, I think for AD, which is the shading device on the north facade of a building in the northern hemisphere, where the sun doesn't shine. Okay, and here we have a real false allegory of science, where we're using we're not styling, we're just using this technical idiom to say, look, my building's energy efficient. I can put this all around the place. So we go from allegory, potentially false allegory, very close to parody, self-parody, and really, my conclusions that architecture sort of reflects the wider sort of contradictions of society. But when we come to computing, I think we think about software as a tool that encapsulates knowledge, essentially potentially frees the user from needing to understand all that knowledge to use the tool, but there may be new knowledge that he needs to acquire in order to be a proficient user. And I want to go back to the ship again, because essentially it stands at the intersection of the sailing and the steam sort of tradition. And if the wind blows from this direction and you're on a sailing ship, you have to adopt this tacking strategy to sail into the wind. You can't directly sail into the wind, but with a steamship you can. And so essentially the steamship means you no longer have to know about sailing. The tool has released you from that obligation, and of course that skill drops. And so there was this saying in the 19th century and 20th century: when our ships were made of wood, our men were made of iron. When our ships were made of iron, our men were made of wood. The lack of the tool embodies so much knowledge that in fact that the knowledge is lost. And of course, in the case of the Titanic, we can go anywhere we like, straight into our iceberg. So we can apply the same thing to computing. This is the Colossus from Bletchley Park, okay, and the same thing. When our computers were slow and bulky, they were used to solve really vital problems, code breaking. Interesting, Dynabook, 1968, Alan Kay and Ivan Sutherland, 1963, and I'm not quite sure when our computers are fast and miniature. I'm not quite sure how to complete that sentence, but we get even more access, but essentially, in my view, to a restricted set of concepts. Accessibility goes up, but what we're accessing goes down, and we get that sort of monitoring, that near monopoly, and it's just amazing that particular kinds of organizations which have a sort of sinister overtone seem to like circular buildings. Not quite sure what that is. Anyway, so we get this sort of invasive approach and the sort of trivial approach, and sort of looking at this sort of trivial or sort of restricted set of computation. I hope that gets projected, but that's visual data flow programming example, and I would call that sort of expedient programming. But I want to sort of go back to some of the ideas of Tom Maver, who was one of the founders of ECADI. He was a person I learned so much from and worked with. And he had a few kind of key expressions, which were, computing amplifies the intellect, and this thing about this using computing in design decision making, that as you measure things and make these things more explicit, the value judgments are forced to the surface, and indirectly they become more explicit themselves, and this is the sort of benefit of that. And then I've looked at the we talk about teaching computation in schools of architecture as though we're going to be the first people to present the idea of computation to the students. But in fact, with the national curriculum, certainly in England, I'm sorry, I didn't know what the national curriculum for computing is in Wales. Sorry about that. But anyway, most probably it's very similar, even better, possibly. Just summarizing some of the bullet points from that national curriculum, it's really teaching people to understand abstraction, logic, algorithms, to analyze problems in computational terms, problem solving, and to actually interesting to use two or more language, at least one of which is textual, not a visual programming language. And I think this is really important, because between the kind of invasive corporate kind of computing and the trivial sort of what can I do with my iPhone, there's a really interesting possibility to do programming. And I had the opportunity to go to the SPLASH conference, which is the conference organized by ACM SIGPLAN, which is the special interest group in programming languages, where we were presenting DesignScript. And Splash E is the educational kind of stream there. And they were talking really interestingly about how to teach computation. It was much more than learning about coding. It was about problem decomposition, recomposition, how to make specifications, how to test, how to design interfaces, encapsulation, reuse, and the idea that you write the program, you encode your own knowledge, and the program should be self-explanatory, or you should at least be able to explain it. And the great theoretician of programming, Dijkstra, this is a sort of reported statement, that a friend asked him to write a program, and he wrote the program, sent it back with this letter, and in the letter it had, if I'd had more time, the program would have been shorter. And this idea of doing something, really refining it, really trying to make the most elegant solution. So I don't know, that has been a theme of, how can we go from the expedient to thoughtful programming? And that's, one of the themes that I try to put into DesignScript, which is now in the Dynamo application. So here's a very simple graph. It's the Axel-Killian standard example, really brilliant. I got my array of points. I've got the control point that I can move around. I'm measuring the distance from that control point to all the other array of points, and then I'm creating a height factor, which is the inverse of that relationship, and then I'm drawing some curves or a surface through it. So that's what it is as a graph. And of course, we can use the node to code to turn that into code. And then, of course, that is dealing with collections of points, collections of curves. And of course, we could expand that into the full imperative programming with for loops and if statements. So these three stages can take the novice programmer through. It can allow him to express something in an exploratory programming way, but it takes him into the proper world of computer science. It doesn't leave him in this simplified, restricted world. And here's a building by Foster and Partners in which this has been used, in this case, to calibrate and measure and color code the different panels on this ocean view skyscraper. And then my colleague, June Mendoza, who was the main developer in DesignScript, who is now working for ARM, has taken DesignScript and this concept of the hybrid visual textual program and has essentially written an emulator for the classic MIPS processor of 1990. So here's the processor. We identify different regions on the processor, different registers, memories, caches, etc. And then they are the different blocks. And he's written the code in each code block to represent that. So you can look at the DesignScript website where all the papers are and user manual in a sort of way which is independent. But I think what I want to kind of talk about here is the certain dilemmas that we have with computation in architecture. So are we making things easier? If you developed a computer system and it didn't make things easier, you'd be in trouble. On the other hand, there's also trouble if you do make things easier. This is the dilemma. Okay, so first of all, what capacities? We should be problem solving. We should be thinking about what does our client want, what kind of building do they need, but we have to learn about the tools. Okay. And if we learn about the tools, then do we become dependent on those tools? Do we start to think about our problem or the solution in terms of the concepts presented by the tools? Do we think about the task more deeply as the result of using the tools? And essentially, we can get trapped in, and in fact, somebody was talking to me about Excel spreadsheets. If you get proficient at using Excel spreadsheets, all problems look like problems that you can solve with Excel spreadsheets. And so the important thing is to become independent of the tool. But the only way to do that is to learn multiple tools. Then you get the problem of, well, actually, weren't we trying to reduce the amount of effort we're putting into tool learning? Oh no, in order to become independent, we've got to learn more tools. So we've got this sort of real dilemma here. So this is a student project that I was involved with at the Bartlett, and I was teaching them DesignScript and Dynamo. And I said, okay, let's do a group project. What kind of project would we like to do? I said, over to you, students. And they came back, we'd like to do, Fibonacci series. Okay, so we've collected our images of, shells and, cauliflowers and cacti. And by the way, the Education Center at the Eden Project by Grimshaw, it uses exactly the same Fibonacci series, although it's in the plan, so you never see it when you go to the building, which is unfortunate. Okay, and they all got out their sketch pads and started drawing, and we can calculate this. This is quite interesting. So how are we going to do this? Okay, so we could just start off by drawing an arc, and then we can project the endpoint, and we can get the next number, and then we can make the next arc, and then now what we can do next is we can copy and paste that bit of code and put it down there, and then we can draw the next arc, and then we can copy and paste that again and draw the next arc. okay, hang on a second, guys, we're never going to get there if we just do copy and paste. There's something more important. If you only have data flow programming and the concept of copy and paste, you never actually discover that actually it's a recursive system. And the famous dictionary definition of recursion is see recursion. But there's I think a really important metaphor here, which is it's the process of embedding ideas within ideas. And so, DesignScript is a recursive program, so we could write our Fibonacci recursive function, which calls itself at the bottom there. It sort of decrements the counter and calls itself. Exactly the same. I actually went to the kind of Wikipedia after I'd written the code and found that it was just it's just the same. But of course, if you only have data flow programming in recursion, this function is going to be called multiple times, so you can't see it in a visual data flow programming because every node only has one state, and that's really great if it genuinely is that each node only has one state. No, this node's going to be calling itself over and over again, and so that's why you need to have a debugger so that you can actually show the students, oh, now you're calling yourself again, and by the way, the arguments you're passing in is one less than the arguments you passed in last time, but and we didn't have. I actually had to take this code and turn it into a PowerPoint and actually annotate the PowerPoint with the values of the arguments, because the debugger is not delivered with Dynamo, even though the language is recursive. And so you can do this sort of visual data flow program. You can park out all your functions on your kind of desktop, and then just have the final sliders and the final execution engine using the data flow, but calling those functions. And then the students wanted to sort of do this Fibonacci series in plan, but sort of roller coaster in elevation, which is really quite good. But the question that I ask is, in the context of architecture or education, what is the result? Is it the visual effect of, oh, I've got this nice Fibonacci curve? If so, just go and draw it. Or is it the ability to abstract beyond the visual? And I think that's really kind of important. So, the expedient programming is good for this exploratory initial. It means that people who didn't think they could program can actually program. That's really good. But it sort of, I think it traps the designers at a particular level of computing. It's got this mentality, oh, I can download this plugin. I'm not quite sure what it does, but I can plug it in, and I've got this sort of hackathon mentality. How can I quickly do something and get some result out? As opposed to the sort of Maver-esque approach, which is, no, I'm really there to amplify the intellect. And, Alan Perlis's remark, a programming language that doesn't change the way you think is not worth learning. So it's really working things out from first principles, and what's the important result is your understanding. And then we come to sort of machine learning, which I think is really sort of another challenge, because essentially people are spending a lot of effort reformatting problems so they can be handled by machine learning. And it may present you with the optimum result, but for my money, it doesn't do what you should learn as a programmer, which is it doesn't provide you with an explanation. And in fact, I've just been as a creator at the Bartlett in the computational course, and people say, oh, I've done this genetic algorithm, and this is the result. Now, why did it do that? And you're spending all your effort instead of solving the problem, trying to reverse engineer how the program actually solved the problem, which it is giving you some reflected knowledge. It's but it's really it's a really very strange way. It's certainly not complementing or amplifying the intellect. So what I was trying to do is to ask, how can we put reasoning back into architectural computation, make that at the center. In particular, how can we make the sort of the fabric the servant of the space? And this is where the work that we're doing with Wazim on non-manifold topology, it's really a system of, like, let's think about the building in terms of the spaces, and reason about them. And please go to the website and download the papers. And I think we're talking about this a little bit more tomorrow. But I couldn't really give a kind of presentation in this building without referring to it. So I got a contact in Rogers, Daniel Wright, and I had a conversation with him, and he sent me some really wonderful images. So I thought it would just be really nice to think about this building. And in fact, it was how it's going up. But anyway, this was the sort of the concept. As it was described to me by Daniel, the architects came up with this undulating surface, and essentially the Arab with the structural engineers, and the Arab sort of exactly in one of my first diagrams did this post-rationalization. They're saying, well, essentially what you've got is this cylindrical surface, the bottom surface, and then it's punctuated with these toroidal patches. And so we're going to rationalize it as that. And then one of them has the funnel going down to the chamber. And I thought this is really, I mean, these kinds of buildings are very symbolic, and I think we're quite good at creating institutions, and architecture is quite good at creating symbolic buildings to match the symbolism of the institution. Okay, and I hope there's nobody here from the Welsh Assembly, because, and this is not Welsh data, this is US federal data from the Pew Charitable Trust, but it says, trust in government, again, near all-time low, and this is going from 58 to 2013. Okay, so even though we're building the institutions and housing them in wonderful architecture, there's something isn't quite working. And so the question we may ask is, how do we build trust? How do we, with the people who use buildings? And one approach is by instead of making the process sort of secretive, I came up with this design, is to actually make it more transparent, and to not just communicate choice and the relationships and the trade-offs that you're making, but actually invite the stakeholders to participate in that. And so I'm going to just show a couple of slides from Dimitri Stefanescu, who is a Ph.D. candidate in the Interchain project at the Bartlett, and I'm one of his supervisors, but this is completely his work. He's written a solution space explorer called Speckle, in which it's not just a solution space. You've got design parameters, which are this is a sort of mixed development of shops and offices, and so he's got different design parameters of the number of floors of housing and secondary development and etc. And then performance measures, floor to area ratio, investment, so and of course this is he's developing this tool. How you use it, what are the design parameters, what are the performance parameters, up to you. But essentially you can select different and this is like move the sliders up and down, rearrange the columns. You can explore the solution space, or you can say, no, I'm not interested in the dimensions of the building. I want to have a building which has got this daylight factor and this energy analysis performance. So you can actually play with the solution. You can filter the solution space or navigate the solution space using performance measures. Because I'm only interested in when I have 5 floors of office space, and so you can actually trace through, or you can actually select and play what ifs in a way where the designer is no longer saying, this is the specific building that I think you need. No, these are the relationships that you can explore to find the building that you want. So, conclusions? Okay, so the first thing I talked about really was this architecture of making, what are the strategies to harness physics or to apparently circumvent physics, sort of blurring the distinctions between performance and persuasion, a lot of the kind of digital decoration, and a sort of more philosophical point. I remember my kind of art history lessons where it was sort of drilled into me that Plato was very critical of art because it interfered with our ability to appreciate nature. And, being a bit radical here, we might say that, computational architecture is not science. It's much more an allegory of science, but it's open to the same criticism that it's interfering with our understanding of science. Some buildings not, like British Museum, yes, but, the one where we've got an arbitrary lump and we're punching holes through it, well, what is that telling, informing the public about engineering and science? And then architecture as computation, are these strategies to amplify the intellect or supplant it? Are we sort of taking a brute force approach where we don't have to reason? And then architecture as emergence. It's a pity that Mike Weinstein isn't here, because I think that so much is focused on how buildings are made, and I think we should be focusing more on how buildings are used. And it's not just beyond that. It's not just the use of the building. It's the process by which the building comes into existence. So it's are we more concerned with technical emergence or social emergence? So I think in the first one, there's a lot of contradictions. In the computation, there's lots of dilemmas, and in architecture's emergence, there's quite a few challenges. So, thank you. Does anybody want to ask a question?
I know everybody had a long day today at the workshop. Does anybody have any burning questions?
Very interesting, Robert. Very, very enjoyable too, especially to somebody who's not sort of working in the field at the moment. At times, I thought I sensed echoes of a call to return to declarative programming rather than procedural programming. Is that a fair comparison?
Yes, I think that that's one area which I would like to add into DesignScript. If somebody said, "What is what would you do now?" But in fact, declarative programming only works if you've got some kind of constraint solver which is doing the work behind the scenes. So it's quite interesting, because in data flow programming, you are actually providing the recipe for, okay, when I move this, I want this to change. In declarative programming, you're saying, okay, I'm declaring these two lines are parallel. When I move this line, this other line moves. When I move this line, the other line moves. So you're actually, you have to either have bought in, if you like, your solver, and there are physics solvers, Kangaroo possibly, or constraint solvers, D-cubed, for example. But interesting, there's a person at the Technical University of Vienna who I met, who is developing a parametric design system that uses declarative programming. I can give you his contact details. I actually sent his details to Rivka Oxman to say, here's something which might work well in the special edition of Design Studies on parametric design thinking. Because, okay, if you're going to think, okay, there's the ready-made, oh, I've got D-cubed, or I've got some constraint solver. But if you're going to define your own, if you're going to declare your own relationships, then that's an additional or another kind of computational thinking that the designer needs to get involved with. So what are these, what kinds of computational thinking are designers comfortable with? And of course, the whole idea here is that we make it more accessible to people who most probably don't think that they're programmers, and then we gradually allow them, or the minority who want to, they can progress and they can discover a broader range of computational concepts and see how they fit into that environment. So what a declarative system would be like, and what kind of thought processes would find that would be comfortable with that, I think is the main question. But very interesting, yeah.
I would somehow follow this up. First of all, thank you very much for your very interesting presentation. And I realized that all the quadrants of computation and integrations are filled. Are we done in the field, or is there anything else that we should do in the future? Or the question is, which are the, besides the question that you asked or the answer that you gave, what are the future tasks that we should work on also with our students and in the research from your point of view?
Well, I think that I would like to see computation used more fundamentally rather than in terms of superficiality, like the facade aspect of that. In fact, I just went to the Fabricate conference, and I met somebody who'd been at the conference afterwards, and he said the problem with that conference was that no one was discussing the architectural concepts. The concepts were somehow kind of established, and it was all about the implementation. And that I think that's a problem, that we've got well, it could be generational, okay, that we've got people just like in that Co-op Himmelbrau example, somebody is like using very conventional, willful, forms of creativity, and then there's another group of people who are making that stand up or doing the computation. Now, maybe if you educate the students properly to combine those two, then you won't get that separation. People will start to think about buildings in terms of computation, and in fact, that's the real critical question. Which Norman Foster gave the keynote speech at the Architectural Geometry Conference, and I kind of slightly provocatively asked him, how has computation changed the way you conceive of architecture? And I think that's the kind of $64,000 question, because it shouldn't just be a faster, more efficient realization tool. I think that's what Tom Mabel was saying. And something that we have never really properly harnessed is the ability of ordinary building users to use computation to design their own buildings. And this goes back to the design participation work that I did with Tom. It's 40 years ago. It's really kind of depressing, all that work. Look at I've got the papers. I rewrote some of the papers. They're on my ResearchGate website. But there, with very primitive systems, we were getting, nursery school teachers to design very humble buildings, little nursery schools in Glasgow. This is not this kind of architecture, but it's architecture that people relate to, and where in one of the case studies that was done after I left, I wrote the partial software, but the project continued with different researchers who did some really interesting studies, and they recorded the computer system was recording what the participant was all the design stages, so you could replay it, and they also recorded the kind of verbal protocol. Oh, I'm putting this room next to this room. Oh, no, I'm putting this room next to this other room. Oh, no, hang on a second. No, I want to have that other way around. And the verbalization of, and they had like evaluative measures. Oh my God, this room's going to be too dark. No, I want some more light in this room. I'm going to change. Oh, now there's a long corridor. Oh, never mind about that. So the actual reasoning that these nursery school teachers were going through to design their buildings was it wasn't, you couldn't say, oh, they're not an architect, they don't know how to do it. But providing a computing tool that gave them the opportunity, I think, is really fascinating and very important. It's going beyond what Speckle is doing, which is saying, oh, somebody's produced this parametric model now, and essentially we define the solution space. Now you, the participant, can wander around my solution space and you can make the value judgments, but there's no real change in rules. In this case, the participant was defining the rules and realizing them as well. So I think there's a lot now. 40 years later, we've got iPhones, and that the idea of computing, of interaction, is much better established, but we haven't applied it back to architecture. Sure. Fine.
I was going to say, isn't one of the things that you can't embed all design decisions in logic? That's like a classic mistake that we're kind of doing when we're teaching this stuff. We're assuming we can make every, like Mitchell, right, used to do, like every design decision we put in these logical steps.
Yeah.
And actually, in the future, presumably, it's how we do some of that, but how we mix it with more kind of, let's say, fuzzy or whatever.
These examples of machine learning or optimization, topology optimization, if you can isolate part of the problem, then yes, but where's the lateral thinking, or where's the subjectivity, or where's the consumer choice in that?
That's the problem, like with some form factors, is they completely dominate.
Yeah.
And you just don't allow anyone else into the conversation that can't do any, kangaroo or anything like that.
Yeah.
Right? Or just
Yeah.
in the old days in the script.
But then you end up with something like the European Central Bank, where you have these sort of two styles sort of sitting together.
Yeah, it's very linearized.
Yeah.
As opposed to actually being a complex mess that actually design
Yeah.
is, right? Other than roofs and
Yeah.
facades.
I think what I would like to see is where there is potential for rationality, and there's it's not tautological, where there's a reason for it. Okay, reason for rationality. We should be using these tools, and where there isn't, we should be very careful about the subjectivity. Why not allow other people to express their ideas?
That's right, 'cause things like that, they're just like one user based. They've always been designed around one person, just like making
Yeah.
opposed to how we code improves.
Yeah.
Anyways.
Yeah.
All right, so we can continue over some food, some snacks, and drinks. Thank you again.
Okay.